All right. Hello, everyone. It's Matt Gonzalez again. And today, for my final paper review presentation, I'm going to be talking about the paper titled The Analysis of the Performance of Earthship Housing in Various Global Climates by Kreis and Huhn from 2007. So, very quickly, just the standard drill, learning objectives, and our topics. I hope that after this, you're able to describe the Earthship concept and how it promotes sustainable housing. I hope that you're able to assess the challenges to Earthship feasibility in different climates. And I also hope that you're able to determine the required supplemental infrastructure to enhance the feasibility of an Earthship in difficult climates. As for the topics, again, pretty standard, just going through an introduction and most importantly, an explanation of the Earthship concept itself, which I haven't gone over yet, and the scope of the study. Then the methods and analysis of the Kreis study and the results and conclusions. So to start, the Earthship as a concept. The Earthship is a concept of sustainable housing development that was pioneered by Michael Reynolds in the 1970s, and this was in New Mexico. Michael Reynolds was a registered architect in the state of New Mexico when he developed this idea of a self-sustaining residence, one that is 100% off-grid and can provide its own water, electricity, and climate control. Of course, to be as sustainable as possible, it's nominally built with as much recycled material as possible. This is mostly in the form of automotive tires, bottles, and cans, like drink bottles and cans. And it is more than just a concept. In the 50 years since the 1970s, there have been many Earthships that have been built, especially in the state of New Mexico. And all those ones on the left there are real ones that you can go visit. And even the top right one, you can tour that in the city of Taos. Now, to see what actually makes an Earthship so sustainable and how it's put together, we're going to look at how it's physically built and what it's made from. So to start from the top down, an Earthship consists of an insulated roof that is a metal panel on top and then rigid insulation underneath and a interior ceiling finish. On the front of the Earthship, this is the south wall in the northern hemisphere and the north wall in the southern hemisphere, is just as much glazing and glass as possible. Nominally, it's all glass on the front. Then around the other three sides are earth-packed automotive tires backed by an earthen berm. So basically, this house is like a hobbit hole where it's built into the side of a small hill. Then the interior partitions in the most sustainable, so to speak, models are also made of recycled materials. This is usually in the form of drink bottles and drink cans, which are packed in with mortar, which is in the picture on the left. And then there are also interior planters which line the front so that the occupants can grow their own food and put use to some of the wastewater as well. And all of this construction, the fact that it's built into the side of a hill, that there's a glass wall on the sunny side, all aids it in being a passively heated and cooled residence, requiring no external energy and no HVAC system. As for the water and the electricity, how the residents can get those two very essential things for our current standard of living is that the water is all precipitation catch water. And the way that the system works is that first water will fall onto the metal pan roof. It'll run down into cisterns, which will hold the water. The cisterns supply the interior taps, and then the drain water is what goes to the toilets and to irrigate the planters. And drain water, also called gray water, of course. And then all the final wastewater goes to septic tank. The electricity is nominally provided by solar panels or PV for photovoltaic, and it can also be provided by any form of sustainable site energy, like wind turbines, for example. But we're going to focus on photovoltaic or PV energy in this particular study. Now, this concept has clearly been thought through and it has been applied, but it's uncertain how feasible the Earthship concept is to provide on a mass scale sustainable housing for typical residents of a developed country. So we want to find out how they compare to conventional wood-framed homes like the one on the bottom left. Can the Earthship provide a similar level of comfort? And is it appealing to a typical consumer who may not be as interested in promoting sustainability as we are, being students in this class? Could they be convinced to live in an Earthship? So the goal of the study is to determine if Earthships can provide comfort of conventional homes at a competitive price, because of course the economic angle is going to be very important. So the methods of the study, how they went about determining this, involved a number of models to evaluate the electrical, water, and thermal systems. The Earthship was evaluated in 4 climates. First, what's called the continental subarctic climate, being in Alaska, the humid continental climate in Michigan, an arid desert climate, which is actually in New Mexico, and then a tropical climate in Hawaii. Now, these are all in the USA because this is a study sponsored by the American Society of Mechanical Engineers. Some general assumptions for the entire study and all models used are that no wind power is used to generate electricity. It's all photovoltaic because there was difficulty in modeling the transients and site-specific nature of wind patterns. It's also assumed that materials are locally available. That poses no challenge to construction. It's assumed there's no solar obstructions to PV panels and they get full sunlight during all daytime hours. All of the Earthships have identical floor plans and they're intended to support a family of 4. Now, the thermal model was generated in Energy Plus commercial software, and this is software that can predict internal temperatures of a building based on input exterior temperatures and a thermal envelope, as we call it, which is just the insulation of the walls, insulation of the roof, etc. The roof, windows, floor, and walls were modeled as in a typical building analysis, and the walls, the exterior ones, were approximated as a layered assembly. That's what goes into this software. That's how typical building walls are thought of, is that there are vertical layers, and each layer contributes some insulation. But in this case, we have these tires that are making up the exterior walls, so it's more difficult to make that case. So it approximated as a layered assembly, which is shown in the figure at left, and the thermal insulative properties were assumed equal in all locales, with some exceptions being that the floor insulation in Michigan and Alaska was higher because of the colder temperatures there and the deeper frost depth, and the area of the windows in those same locales was smaller because of the intense sunlight from the low-hanging sun in higher latitudes in the winter. And the thermal comfort level that we want to be aiming for in the Earthship is going to be 70 to 82 degrees Fahrenheit, which is considered comfortable for a typical family in America. As for the electricity, there are some assumptions made about the demand. First of all, it's assumed that the occupants are making attempts to be conservant by using Energy Star appliances, and that it's also assumed that the worst case demand occurs every day. So this is depicted in the figure at left, which shows a worst case demand day, and it's assumed that there are never any vacations where they're away from the home and electricity is not used, or days where they're using less or anything like that. It's always going to be this worst case. The power generation was modeled in a commercial software as well, being PV Design Pro S, and this is just a software where the user can develop a PV system and then see how much electricity it's generating. So at the end of the day, it's just a matter of designing the most efficient PV system for each locale and then making sure that it exceeds the demand and then seeing how feasible that is, which is what we'll talk about, of course, in the results. Now, as for the water modeling, the assumptions on the demand are that the occupants are again conservative and are making efficient use of their water and using efficient appliances. And it's also assumed that all gray water is recycled into the toilets and the landscaping, as we discussed before. So if you look in the figure at left, There is the average US family on the very far left bar in this figure. Then in the middle is an average US family who is making attempts to be conservant with their water. And then on the right is the Earthship demand, which is the same as a conservant family, but now the toilet and landscaping water is no longer factored in since that is coming from gray water. So the supply is a pretty simple estimate. It's just coming from the yearly rainfall depth in each locale and the area of the roof. So the depth times the roof area will give a volume per year. And it's assumed also that the cisterns are able to hold any excess water from wet seasons indefinitely so that they can give that water back in the dry seasons. Now, the financial model is a pretty typical net present value analysis. A conventional wood-framed home and Earthship's life cycle costs were compared. At a 6% discount rate, inflation and market changes are included in the model. Market changes meaning how the price of electricity is projected to change over a 45-year life, which is the lifespan assumed for each of these homes, 45 years. And then it's also assumed that the floor plan of the wood-framed home is also identical to the Earthship. The costs that are factored into this analysis are, of course, design and construction for both Earthship and wood frame. Then there's also the cost of gas, electricity, and water for the wood frame house, only not for the Earthship. And then the battery and PV system replacement for the Earthship home is another cost that's included there. And then at left, we also have a table showing the assumed prices of utilities in 2006 dollars. And there's also an additional cost of $1.06 on water in the wood-framed home for a sewage service fee. And that's all going to factor into the lifetime cost over 45 years. So the results of the study, to start with thermal comfort, the Energy Plus model was validated and determined to be adequate with data from a real Earthship in Gumerco, New Mexico. And it was seen that the comfort level that was being aimed for, 70 to 82 degrees, was maintained in the summer months. And you can see this in the figure at left, where basically that big black smear is the temperature envelope for each house from Energy Plus analysis in the Earthship. And in all four cases, it is falling right squarely into our comfort range in the summer months. Although New Mexico and Hawaii exceeded the comfort range in the winter because of the intense sunlight with the low-hanging sun in the winter months, and Alaska and Michigan fell short of the comfort range in the winter because it just gets so cold there. So this shows us that to meet the requirement, supplemental gas heating is required in Alaska and Michigan. As for electricity and water, the PV systems designed from the software analysis were put together to meet demand and then priced to see how feasible they were. And we will see how realistic it is once we get to the financial results. As for water, water demand exceeded the supply for a family of four in all locales except for Michigan, where it's obviously very, very wet. And this shows that for the family of four, supplemental water is going to be required. Now, in the financial results, the analysis was tweaked a little bit to make things more realistic for the Earthship construction. The Earthship design was altered to meet the requirements, so grid electricity to replace photovoltaic was considered where photovoltaic costs were very high. Water was supplemented by a city water connection, and gas heaters were supplied to the Alaska and Michigan Earthships. Then a off-grid, grid-attached Earthship and a conventional wood-framed home were all compared in terms of their life cycle costs. And on the left, you can see the results where you basically have each line being the cumulative costs for each of the options. And we can see that the standalone Earthship is very, very expensive because of the upfront cost of installing solar power. But a grid-attached Earthship is more sustainable and more economical, actually, than a wood-frame home, except in all cases, except for in Hawaii, where it's very, very nearly even in cost. So the conclusions based on all these results are that the Earthship is not yet fully practicable for widespread application and sale to a conventional American family, and supplemental infrastructure will be required to meet the expectations of a typical American family. This is not to say that the Earthship isn't a good idea and that it's not perfectly comfortable to live in if you're willing to compromise on some of the amenities of a wood-framed home. But in terms of a mass distribution and basically a replacement of existing homes at the same standard of living, it's not quite there yet. But it is, of course, speculated that the feasibility of self-sufficient models of Earthships will improve with technology as photovoltaic systems become more affordable and so on. And this is the citation of the paper, and thank you for watching.